Our first speaker is Stefano Giorgini, who will tell us about that.
Okay, so good afternoon, everybody. It's really a great pleasure to be here and to participate in this interesting conference. And so I should thank Andrea and David for arranging and organizing such a nice conference and for giving me the opportunity to be here. It's my first time in Camerino and I really enjoyed this day and the conference. So thank you. So what I'm going to talk about is I'm going to report on some works we have been carrying out in the last couple of years together with Natalia Bikieva, who was a former PhD student in Trento and former postdoc. Yes, former postdoc. And so the work is done at the DEC Center in Trento, and I'm going to talk about the quantum Monte Carlo study of dipolar fermions in single and bilayer configurations. I will take advantage of yesterday's talk by Silke, who already explained some of the experimental problems and experimental issues in creating dipolar molecules. So I would like instead to, so since this is it's more an interdisciplinary conference, I would like to convey what are the interesting many-body problems with dipolar interactions. So first of all, of course, the main novelty about dipolar systems is that the dipolar interaction is long range and anisotropic, and this is in contrast to usual interactions in cold atoms, where the typical range of interaction is about 10 nanometers, is the typical range of the van der Waals potential, and then the temperature of the system is so low that usually everything is well described by just the S-wave scattering length, and so the interaction are spherically symmetric. Instead, with dipoles, of course, you have anisotropy. So here is the interaction potential between two dipoles aligned in the z direction. And here D could be either the electric dipole, if you think about molecules, heteronuclear molecules, or could be the magnetic dipole, if you think about magnetic atoms. And then there is a typical length associated with the interaction, that is the mass of the particles, the square of the dipolar moment divided by h bar squared. And so this is the typical length scale associated with this. And of course, in the case of fermions, we would like to compare this length scale with the inverse of the Fermi wave vector. And so when KFR0 is large, it means that you have large effects due to dipolar interactions. And so this is completely new in systems of cold atoms, and then the question is whether this leads to new interesting many-body physics. There is a fast experimental activity, fast progressing experimental activity. We already learned from Silke yesterday some of the experiments here, and I would like just to stress that you have two different categories of experiments. One is heading towards atomic species with large magnetic moment, and so this goes back to the first experiments by Tillman Fau in Stuttgart, where they used chromium. Now there is dysprosium, and more recently erbium in Innsbruck. But here the magnetic moment is about around 10 Borg magnetons. And so if you turn this into R0, this is quite small. So it's on the order of a couple of nanometers or tens of nanometers. And so if you compare with the typical density that you can reach in fermionic systems, then KFR0 here is from 0.01 to 0.2, so it's again quite small. So really the breakthrough would be to create heteronuclear molecules in the low vibrational ground state and in the degenerate regime. And so here, I have a list, but this is not complete, as we understood yesterday from Silke. There is potassium rubidium, where the electric dipole is as large as 0.6 dBs, so we are already in the range of R0 on the order of 600 nanometers. Then, so with sodium potassium, it goes to about 10 microns, and then the best candidate would be lithium-6 cesium, where R0 is about 60 microns. And so here, clearly, KF0 could be as large as 600, so huge effects of dipole interactions. And so, as we understood yesterday from Silke, two-dimensionality is crucial, apparently, in dipolar systems. One problem is the bad chemistry that you have, for example, with potassium rubidium, that you form molecules plus energy, and this is bad if the molecules, so if the dipoles can approach each other. Apparently, you have mixtures which have not this problem, but as we understood yesterday, you have problems of sticky collisions, and so it's crucial to keep dipoles far apart. And so that's why two-dimensional systems where you have an external field that aligns the dipoles perpendicular to the plane could help with this bad chemistry, and also in general helps the stability of the many-body system, because otherwise you would have problems of collapse. So that's the configuration that is most natural in these systems, two-dimensional. So the dipoles are confined on a two-dimensional plane, and then you have an external field that aligns the dipole either perpendicular to the plane or at some tilting angle, theta 0. And here is the interaction between two dipoles with an angle, and you see that if the angle is 0, then the interaction is purely repulsive, of course, but then if you have an angle, at some point you have a critical value for this angle at which you start having an attractive part in the XY plane. Okay, so let me just go through some of the interesting issues concerning many-body. So if you deal with bosons, one first thing that is interesting is the creation of the possibility of having rotons if you are in a quasi-2D geometry, and your density oscillation, so the wavelength of the density oscillation is on the order of the transverse confinement. You can have this interesting feature of the elementary excitations that you have a roton-like structure as in liquid helium. If you instead go to purely 2D systems, it's predicted a transition from a superfluid to a crystal phase once you increase the density. And here you have the whole problem of whether you can have room for an excitic phase. We know that in 2 dimensions, melting of a crystal happens through an excitic phase, which is predicted at finite temperature by Nelson and Koster-Ritz-Dowless. And so it could be interesting to see what happens in the generic regime, whether this excited phase exists. And so the only experimental evidences of this excited phase are actually for classical colloidal systems. And so it would be interesting to see what happens once you include quantum operations. Then, of course, you have the whole bunch of lattice systems that you can come up with dipolar interactions, because you can have all sorts of nearest neighbor interactions, and there is a nice review paper that I quote here. Then, okay, the case of fermions, again, you have many interesting possibilities. You can consider a single layer, and here, okay, so if the interaction is weak, you have a Fermi liquid, then you can play with the tilting angle, and so if the tilting angle is large enough and you enter the regime where you have an attractive part, then you have, of course, pairing, and this pairing will be P-wave, and so you have the possibility of creating a P-wave superfluid. Below this critical angle, you still can have a charge density wave state, a stripe phase. So here is depicted a sort of midfield phase diagram for this system. If you have a tilting angle, at some point the fermions would prefer to align into lines in order to maximize the attractive part of the dipolar interaction projected on the plane. And then, of course, here again, you can have a Wigner crystal once the density is large enough. Then in the multi-layer configuration, so you have the same system, but now 2 layers, and you can easily make the barrier between the 2 layers in such a way that there is no tunneling, so that the confinement is strong enough that there is no tunneling. And here you have a fermionic system up here, a fermionic system down here, and of course you have attractive interaction between the layers, and so you have a novel type of BCS-BC crossover as a function of the distance. And this is in analogy with the electron hole bilayers that we heard about today. Okay, so I would like to stress also analogies for the single layer with the 2-dimensional electron gas. So here is the phase diagram as a function of 1 over Rs. You should consider that in the case of Coulomb, the role of density is inversed. So the Wigner crystal happens at low density, while in the dipolar case happens at large density because of the nature of the Coulomb interaction. And so this is a phase diagram in a paper by Clark, Sepperly, and co-workers, where they investigated the phase diagram. They could find an excited phase in this region, and instead they looked at also the quantum phase transition that you have between a Fermi liquid and a Wigner crystal, where again theories predict that you should have the transition cannot be first order, but you should have some intermediate phase, microemulsion phases made with stripes and bubbles. But so this calculation was not able to obtain those exotic phases. Okay, so let's go to the first thing we studied, that is the single layer with fermions. Okay, so we have a two-dimensional, purely two-dimensional system of dipolar fermions with an external field that aligns the dipoles perpendicular to the plane of motion. So the Newtonian is written here. You have the kinetic energy of the n fermions, and the interaction is purely repulsive and 1 over r cubed with the dipole moment. Okay, so you have one-dimensional parameter that is the product of Kf and R0, the length scale, which are reported here. Kf is the usual wave vector in 2 dimensions. And what the method we use, and here is the only place where I say something about the method, probably. We use the fixed node diffusion Monte Carlo method. That is a projection method. You start on a trial wave function, and then by applying iteratively the evolution operator in imaginary time, you can filter out the ground state. This is exact for bosons. Of course, in the case of fermions, you have the sign problem, and so what you do is you make an answer for the nodal surface of your trial wave function, and this is kept fixed during the calculation. And so what you get is not the exact ground state, E0, but you get an upper bound within the class of wave functions that share the same nodal surface. Okay? Right, so just to show you, so for example, so that's very useful because you can, in principle, decide what phase you are looking at by choosing the nodal surface. And for example, here we show what we do to simulate the Fermi liquid phase. We use a product of Jastrow terms, so where you have a product over all the particles, times as later determinant of plane waves. That would be the nodal surface of a free gas of fermions. So the usual later determinant of plane waves. Instead, for the Wigner crystal phase, we use the same Jastrow factor that accounts for correlations between the particles, but then the nodal surface is imposed by this determinant, and here you have an anti-symmetric combination of Gaussians centered at the center of your Wigner crystal. Okay, and so you can see here by looking at the pair correlation function that indeed we simulate the liquid or the crystal. And then, okay, so we calculate the energy, and here is the equation of states as a function of KF0. At low density, we find agreement with R3 theory, but you can also include beyond field corrections, and we have good agreements. And then by increasing the density, okay, so the energy goes down in these units, and then here the triangles would be the result for the Wigner crystal. So at this point, you see that there is no, you should make a zoom that is done here. So the blue points is the difference between the energy of the solids and the liquids. And you can see that at some point the energy of the solid becomes below the energy of the liquid. And so you have a first order within this approach phase transition between the liquids and the solid. And so we predict that this phase transition happens at KF 0.25. In the case of bosons, this was much larger, was about 60. And by doing the Maxwell construction, we also find that the coexistence region, the region where the two phases coexist, is quite small in terms of these parameters. And then this puts some limits on the possibility of having these exotic phases like a stripe phase or a bubble phase, because they should happen. Of course, we cannot exclude those phases. We cannot see them, but it's believed that if they happen, they should happen in the region of coexistence of the first order. And so the region of parameters where they could exist should be quite small. I would like to point out also that here, at large densities, we find agreement with the prediction for a classical gas. So this is the theory that you can build up starting from the classical energy of a Wigner crystal, including the 0-point motion of phonons. So the Wigner crystal, the classical energy would be down here, but then if you include the 0-point motion of phonons, you get this line, and you see that we are approaching this. But I would like to point out the large effect of phonons. So this Wigner crystal is really a quantum crystal. Okay, then the second problem is approaching the problem of the bilayer. We consider the simplest problem, that is a single impurity in the second layer. So you have the same fermionic system in the bottom layer, and we add a single impurity in the up layer, and there is no possibility of tunneling, of course. So then the Newtonian is now the same as before, but now you have the interaction between all the particles downstairs with the impurity, and the potential is like this. It's a potential that is attractive when the two are on top of each other, and then becomes repulsive when the two are far apart. And here an interesting question is to, so first of all, I should say that if you take two particles, one in the bottom layer and one in the upper layer, there is always a bound state. For whatever distance lambda you put between the two, there is a bound state. Because the problem is two-dimensional with a slightly attractive potential, so there is always a bound state. This is crucial. And okay, so our many-body problem depends on KF0 in the bottom layer and KF lambda, that is the coupling with the impurity. And we calculate the binding energy and the effective mass of the impurity. And as you can see, it's an interesting problem because it's a sort of Polarov-like problem where the impurity could be either coupled to fermionic degrees of freedom, where in the bottom layer you have a Fermi liquid, or to bosonic degrees of freedom, when in the bottom layer you have a Wigner crystal. And indeed, if you work out the effective Hamiltonian when the distance between the two layers is large, when KF lambda is large, you can directly work out that your effective Hamiltonian is of the Fröhlich type. Right? So you have the classical energy of the Wigner crystal, the phonon contribution of the Wigner crystal, that's the impurity that lives in a periodic potential, and then this is the coupling between the impurity and the phonons that are described by this in the Wigner crystal. So it's exactly a type of Fröhlich Hamiltonian with this is the Fourier transform of the interlayer potential that depends on lambda exponential. Okay, So you might think that this is a very beautiful example where one could study the localization, the possible localization of the polaron and the consequences of Landau-Becker theory. And okay, so this is what we did. We calculated, in particular, the effective mass of the polaron by looking in Monte Carlo simulations at the large time diffusion constant of the impurity, which in general behaves like this as a function of imaginary time. So if you had a non-interacting particle, you would have this thin dashed line, but then increasing the coupling between here is you reduce from the pink results the distance between the two layers, so you increase the coupling. You can see that the diffusion is slower compared to the free particle, meaning that the effective mass is large. And here are the results. So those refer to the impurity coupled to the Fermi liquids, and so the inverse effective mass starts from 1 and then increases. The inverse effective mass decreases and goes up to a value that is even larger than 2. That is what we would expect if you had pure diamonds. And instead, in the case of the Wigner crystal, the effect is more dramatic, and you can see it here as a function of KF0, and you see that the effective mass becomes way larger than the bare mass, orders of magnitude larger. But so here the important thing is that this is not what we expected, it's not the Landau-Becker localization, and indeed phonons have exactly the opposite effect compared to what one would expect. So in the Landau-Becker picture, you have that phonons should dress the impurity and so increase the effective mass. Okay? Here instead we see the opposite, so we could do the calculation with just the static potential, so phonons are frozen, and the result would be like this. So then it means that phonons here reduce the effective mass compared to the purely static potential. So you have a sort of phonon-assisted hopping that is very important. Okay, so I think I just say a couple of things about the fermionic bilayer. So now you can add more impurities or more fermions to the up layer, and you can investigate what happens to the equational state and the gap. And let me just flash the results for the gap. So we, in diffusion Monte Carlo, one can calculate the gap both by adding one particle and looking at how the energy changes by adding or removing one particle. And so you see that if you add two particles, one in the up layer and one in the bottom layer, you pay twice the chemical potential. But if you add only one, you pay chemical potential plus some extra, that is the gap. Or by another way of calculating the gap is by unbalancing the population of the up and the bottom layer, keeping the total number of particles constant, and so calculate the energy as a function of polarization. And again, if you have a term that is linear in the polarization, the coefficient in front is exactly the gap. And here are the results for the gap as a function of kf lambda. And so we compare here with mean field theory, that is the simplest mean field theory that neglects intralayer interactions, and we see important deviations compared to a mean field, especially when the distance between the two layers is small. And with this, I would like to, okay, that's the summary. Unfortunately, I do not have time to discuss more in details this novel BCS-BC crossover, but I just would like to thank you for the attention, and that's our Trento BC group that is.
Thank you.
Okay.
Any questions?
I guess you used the term by analogy for the phonon and phonon-assisted hopping, because you don't have phonons here, but if that analogy...
You have the phonons of the crystal, of the linear crystal.
Oh,
So you have a, so it's the, okay, so
but what temperature is this at?
this is zero temperature. Zero temperature. So you have quantum fluctuations of the formats. So this was what I was emphasizing at the beginning. You see that here the quantum effects in this crystal are very large. So you have such a jump in the energy, considering only the classical energy of dipoles at the equilibrium positions, or you have the zero-point motion of phonons, which gives you this energy here. Okay. And then in the quantum Hamiltonian, okay, so you have the zero-point motion. So what was giving that jump is h bar omega qs times 1/2, is the zero-point motion of the phonons.
Can you add some other comments on the non-monotonic dependence of the gap as a function
Okay,
of
so
the
yeah,
lambda,
that's a
and
bit-
also would like to know the normalization of energy, because I was
Yes.
not able to see well.
Yeah, so okay, so
Mhm.
okay, so those are the results for the equation of states. So this is the total energy per particle in terms as a function of the distance, and you can see that in the BC regime is dominated by the binding energy of the dimer. So the green line is the binding energy divided by 2. So here the energy becomes large and negative because the dimer has a large binding energy. So then what is interesting is to remove this trivial two-body term from the energy per particle and from the gap. Okay, so that, for example, if the equation of state, once you remove the two-body contribution, would look like this, where you interpolate essentially from the energy of a single layer, fermions, and the energy of a single layer of composite bosons with mass that is twice and dipole moment that is twice. So you have to rescale the energy, but then you recover exactly the energy of a single layer of composite bosons compared to the mean field that would give you 1 always. And the same is for the gap. Of course, here again, the gap, you subtract the trivial contribution from the dimer. Otherwise, essentially the gap would follow the half of the binding energy. But this is trivial. So it's a two-body, just a two-body effect. It's relevant to remove this from.
Okay, short question. Could you please go back to the fact you must have over? You have these
Yes.
slides. Is there any way to determine whether it is a critical value of this parameter where you jump from one situation to the other?
Well, this is when when the phase transition from the liquid to the crystal happens.
Can you see from it just
Yeah,
as
yeah. So it's you can see that.
there is an edge jump?
Yeah, so it's the transition is so there is 20 is still liquid,
Yes.
28 is a crystal. So if you fix kf lambda and you change kf0, you will have a jump at the crystal, at the crystallization depth.
Bell is ringing, so I guess we should move on.
That's like
Okay.